Hi there, let's begin with Chapter 1, Introductions to Vibrations, where we are going to discuss some fundamental terminologies and their definitions. In a vibrating system, there are three important elements we should identify. The first one is the mass, which relates to the motions of a rigid body. And this mass stores the kinetic energy. The second one is the stiffness, which corresponds to the deflections of a flexible component. And this stiffness component stores the potential energy. The third one is the damping, often illustrated with a dashpot, which can absorb vibration energy. Now, assuming there is a centrifugal machine mounted on a flexible rubber attached to a rigid floor and vibrate vertically, say with amplitude x, the whole body of the machine which is moving up and down can be defined as the mass component. The rubber mounts which can stretch and suppress as the machine is vibrating can be defined as the stiffness component, and the rubber mounts has also its own damping mechanism, and this can be defined as damping component. And this diagram model, we call it the mass spring damper model. Now let's look again at the machines mounted on a flexible springs on a rigid floor, vibrating with maximum displacement from the equilibrium positions O. The amplitude is defined as how far the machine displaces from point O to A, or from O to minus A. Meanwhile, the frequency is defined as how many times the machine goes in one cycle from O to A to minus A and back to O in 1 second. The more cycles the machine has in 1 second, the faster the motion of the machine. One complete cycle in 1 second is defined as 1 Hz. The phase describes the behavior of the motions. Let's say that the left hand side of the machine is P and the right side is Q. If they move in opposite directions, we say P and Q move out of phase or has 180 degree phase difference. Okay, so let's write down the amplitude of the vibrating system as the functions of frequency and the phase. As xt equals to A sine omega t plus phi, where A is the maximum amplitude, omega is the frequency, and note that the omega equals 2 pi f, where omega is in radian per second and f is in hertz. Phi is the phase, also in radian, where 1 radian equals to 180 degree over pi. Let us now plot the functions of xt a sine omega t plus phi for phi equals to 0. This will actually be a sine functions with maximum amplitude A across the omega t, and the distance from peak to peak is 2 pi. Well, this can be obtained with the fact that omega t equals 2 pi ft, where f is 1 over a period, and the time taken from peak to peak is a period, so we finally get 2 pi. Now say this curve is P, and we add another curve and name this one Q. This is shifted by pi over 2, so we can see that the peak of the curve Q comes later than the peak of P, we say Q lags P by pi over 2. Now if we shift the curve Q to the left with also pi over 2 difference, now the peak of Q comes earlier than the peak of P. We say Q needs P by pi over 2. If we shift the curve further so that the peaks of both P and Q are one at the maximum and the other at the minimum, we say Q and P are out of phase or differ by pi radian.